Hi, everyone, and welcome to my talk. We are just getting started. There we go. All right. Welcome to the basic of profiling, where I try to explain, well, the basics of profiling, exactly that. This talk started roughly kind of a year ago, actually. I was at CppCon last year. I was making a talk about a game I was working on at the time, Stellaris, and explaining how I managed to make the game start much faster, doing some tips and tricks about the concurrency model of the game. So it got positive reception, at least I think so, but this slide caught the attention of a lot of people. This slide, which I just show a basic profile of the game and how I analyzed basically the effects of the threading and the concurrency issues the game has had. This sparked more question than the talk itself, and we ended up, I think, in Remo after the talk, talking for the last half an hour on how I use the tool, and I basically end up doing a live demo. I think no recording has ever been made because it was just one throwaway thing in the conference room. And so this year I'm back, and I'm back with basically kind of that small introduction, but as a more structured talk, and hopefully you will be able to learn something today. So last year was about, hey, here's how I make things faster. This time it's here's how I made things firmware was slow. This is not from me, by the way. I would like to thank the anonymous commenter that reviewed my abstract and suggested that the profiling was not about explaining how you made things faster, but how you found what was slow. I found it's a great quote. If you are the person who made this quote, please contact me so I can attribute it to you. But I think it's a very good description of what profiling is about. So hi, for those who don't know me, the name is Mathieu. Mathieu, if French is not your favorite language. I'm a tech lead at Paradox Development Studio here in Stockholm. And I work on Hearts of Iron 4, which is a World War II grand strategy game. I previously worked on Stellaris and European Universalis 4, which are two others of our games. You can reach me at a bunch of different addresses and media system. I will be having a second talk tomorrow about the way our game actually work threading wise, if you're interested. It's going to be at 3:30 Stockholm time, if I recall, which is something else, Mountain Time. Sorry if my translation of time zone is not the best. Also, we may or may not be joined by my extra Quantic speaker, Max. He has a tendency of jumping on my keyboard, and since this is still working from home, we might get a few surprises, but no guarantees. So what about this talk? So it's about profiling, of course. You can come as you are. You don't need to bring anything with you. I will try to cover the basics of profiling. If you have never opened a profiler in your life, you should be at ease. And even if you have, hopefully you can still learn a thing or two. Can I show the cat at the end? Question from already a question. Can you show the cat at the end? I will try. He has a window open, so he can go in and out and hopefully do not take too much time of us. But if he's there, I will absolutely come and salute the public with him at the end. Promise. So we'll talk also about the tools for profiling. So basically the different profilers, which is basically the tools you use to profile. I'm using two in my examples, which is the one I use all the time. There are a million others. It's more about finding the one that works for you on your platform and that you appreciate using. And also we were talking a lot about building an intuition, because there is a lot of there's a lot of things that happens in a profiler. There's a lot of numbers. There's a lot of outputs, and there is some part of intuition to develop, some kind of an art, I guess, about how to be able to interpret the data, basically. So let's start with the basics. Just a bit of theory. I have like 1,000 slides on it, and then we can jump back into practical cases in which I even have a few live run through of a provider. So I think we've all heard this quote. It might be the most overused quote in the whole of programmer and computer science, but I found it particularly true for this case. So the quote goes, the real problem is that programmers have spent far too much time worrying about efficiency in the wrong places and at the wrong times. People say it's about premature optimization. I think it is probably true, but today I would say that it's also about the fact that people sometimes try to optimize without using a profiler. And what's the problem? Why do we profile? It is extremely difficult to figure out why a program is slow, especially a modern application that has lots of moving parts, potentially thousands, hundreds of thousands lines of code, hundreds, thousands of files, different modules, a lot of different things going on, but potentially some IO, different threads. It is difficult to reason about and just say, okay, this is probably why this is slow. You can say this is probably why this is slow, but this is just a guess. And basically, if you just try to figure out why it's slow by reading the code, you might get lucky. You might. But there's also a high chance that you will spend a lot of energy optimizing the wrong things because they're actually not what's making your thing slow. For example, the thing I showed last year with Stellaris, I didn't just invent it. It was really shown to me by a profiler. And finally, modern CPUs are quite complex. I think when this code was written, people were running on like much more simpler one instruction equals one or several cycle systems. Today, the same instruction can get you 1 to 100 cycle difference with the exact same code, just depending on cache and branch prediction. There is pipelining going on. Most CPUs have several cores now. There's a lot of things. There's a lot of moving parts. It is getting harder and harder for us to just be able to have a mental model that is not just a very, very crude approximation of what's actually happening, and so mostly wrong. So at the end of the day, measurements. I think in this talk, you will hear a lot of things that are very close to what people say when they do optimization and in talks about performance and optimization. Measurement is key. You cannot, you can make a lot of assumptions, but you need measurements to validate them. So what are profilers? Profilers are tools that are helping the programmer measure and reason about performance. It's really that. You measure the performance, especially you reason about the performance. So when you're trying to optimize something, the usual cycle goes like this, right? You start by measuring. Always, 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 when you're trying to profile and optimize, you start by measuring. So you measure a test case, whatever test case you're trying to improve. You measure it. And then you look, okay, what are the numbers? Am I happy about them? If we're happy, cool, we're done. Cool, we can stop right now. And my talk is over in 7 minutes. But often you're not. And so you need to optimize. And then you optimize something, and then you measure again. And then we loop. And then we see if we are happy or not. And that we go over and over again. And that's basically it. Where do profiling come up in this thing? I would say mostly in the optimize phase, which is we're unhappy about the performance that we have measured. We're trying to figure out what is slow. We use a profiler to help us figure out what we should optimize. We optimize it, we try again. You can use a profiler if you can use a profiler to measure. It is possible. Oh, and here is Max. Excuse me, Max. My co-host has just joined. So as I was saying and explaining to Max, you measure most of the time with something external, but you might be measuring with the actual profiler. It is possible, although I would put a small warning on that. Profilers may have may create observer effects basically on the measurement you're doing because they're using resources to measure. They're introducing some side effects that might actually skew the measurement. So it is an okay measurement, but it's not the best measurement. It does not replace an actual run it live and see if it's actually good enough. And someone is asking me, how do you know if you're happy? This is a very philosophical question that I think philosophers have been pondering for centuries. But if we stop at only those slides, it is actually something that I'm going to touch on a bit later, which is you have to define an objective for yourself. Else you might end up just stuck in this loop forever. All right. So, Max, look at the camera, Max. See, he's there, likes optimization and profiling. So, profiler and optimization. Basically, profilers are one of the tools you can use to during an optimization cycle. They're used to investigate where to optimize, as we just said. You can use it for measurement, but it has some limits. So what do you use a profiler for when you're trying to do an optimization cycle? Basically, you use it to identify hotspots and bottlenecks, figure out where your attention should be spent. You use it to visualize the execution timeline and figure out what sticks out. Basically, we'll go back to this. You can collect a lot of metrics. You can make averages. You can extract the min, the max, the median, a bunch of other stuff. You can also collect a very low-level CPU metrics that are now published on modern chips, like the frequency on which you miss the cache and you have to go to main memory, or how often your branch predictor is wrong, that kind of thing. There's two types of profiling. There's two big families of profiling tools. We use different technology. I'm going to try to talk about those two. The first one is sampling. Sampling is simply you attach to a program, periodically you interrupt that program, and then you record the stack trace. You do that at a customizable frequency that is usually 1,000, 10,000, 100,000 hertz, depending on how much precision you need. The more precise, usually the more side effect it might have on the actual measurement, because you interrupted the program more and more often, and you might be triggering side effects by doing that. And basically, by doing a lot of those and then computing a statistical average, you can get a pretty solid idea where is your, on average, if I interrupt your program, where is it? And that tells you, well, if most of the time, or if 20% of the time, when I'm interrupting your program, it is in this function is roughly taking 20% of your CPU. This is not the entire, I hope you can appreciate the difference between the two. This is not entirely equivalent, but it is close enough that you can rely on that to as a significant average that you can use to say, okay, there is something there that is happening. And it is taking roughly 20% of the execution time, for example. An example of that such tool is vTune. It's the one I use for that. It has a lot of metrics. It's made by Intel. It is free as far as I know, and it can give you scores of data and metrics about how your CPU is doing. It is extremely simple to implement and start using, because the only thing it needs to be able is attach to a process and read the stack trace. So as long as you did not remove the symbol table and the ability to, even without the symbol table, you can do it. It's just usually not useful. But as long as you can get the symbol table and you're able to walk the stack. So basically the program has not been made with like the optimization that removes the stack frame. You can profile the program. You don't need to recompile it. You don't need a special build. You just run it and you're done. If you have like the PDBs or whatever debug infos, you can get a few extra data out of it, but you really need a minimum amount of debug info. You can probably do it even on an application that you don't have access to the source of the debug info, and you will get something. Yeah, the big thing is it works out of the box on any executable. You don't need anything special. It can even be run by someone who doesn't have access to the code. A small drawback, of course, especially in optimized build, is that inline functions are usually invisible. So if you have a lot, if you have, for example, like if you have a container in your code that is not efficient, like a homemade container that turns out to be not efficient, like in an operator square bracket, for example, those are often very well in line by compilers. You will not see it. The impact of using that container will be spread out across all the code that uses it. You might still be able to see it when you look like at the breakdown line by line, which we'll see later, but it's not as much obvious that it sticks up at the top. Hey, 20% of your program is spent doing operator square bracket. There's probably something wrong with it. That bit you will miss. The alternative is instrumentation profiling. It's called instrumentation because you add code hooks in some places of your code, most of the time a macro, to say, hey, I want to record that I'm entering this, I'm creating a stack frame here. which doesn't have to be an actual stack frame. You can start it at any point in the block, basically, or at any line. Just say, hey, I'm entering a section here. You're basically creating your own stack of execution, and you're telling the profiler, hey, I want this to be considered an event with its own breakdown and frame under it. Since every call is recorded, because basically you increment a counter every time the code is run through, it is not based on statistical averages. You get the exact data. You can then do an average if you want to see like a condensed view. But the very important thing is that if you have outliers, they stick out extremely well. For example, if you're analyzing, let's say, like some kind of web service that keeps like processing requests, and 1 in 100 requests is extremely slow, but all the others run in normal time, there's a high chance that the sampling profiler will not show it, because due to statistical averages, it will just be completely lost in noise. If you have an instrumentation profiler, you will see your 100 frames, and you will see that one of them is like 10 times slower than the others. And basically, yeah, you will be immune to statistical anomalies. You will be immune to problem created by inlining. Optick is a great example of this. It's the one I use. We'll have a demo later. It is a bit heavier to use, of course, because as I said, you need to have collection macros in tactical places in the code. If you start from 0, you have nothing. So it's up to you to go through all your code and place it where you think it is necessary. On the plus side, since you are the one writing the sampling and the instrumentation calls, you can supply extra business metadata. If we go back to our example of having one request that is much lower than all the others, if you have some business metadata attached to each request that is profiled, and you see that one of them sticks out, maybe just by looking at that data, you can already figure out something is wrong. Like, for example, it's a specific client or a specific type of request that is much lower than all the others. And you can immediately say, there's probably something wrong with this client or this product or whatever it does. And finally, the modern ones, like Optick, they can fall back on sampling, which means if you get under, if you are under a recorded instrumentation frame, it can still be able to do sampling, and then by walking up the stack, figure out how close in which instrumentation frame it is, and then give you a breakdown. So even if you don't know exactly because you didn't add some metadata to that particular area of the code, you can still get a rough breakdown again based on sampling to get an idea of, hey, what's roughly happening there. It's not as perfect, but for example, it can give you an indication that you should probably be adding a few manual instrumentation things to those functions. It has build implication. And if you know me, you know that sometimes I like to talk about build. And yeah, it means you have to pull a third party in your code base, headers, and also library to some extent, and you have to link it. So it is not as trivial. And it also means that you probably need a special build that you ship only for that matter, and that you will probably completely macro out, if def out of your normal release builds. So this is the one slide that summarized both of those. Do not feel bad about mixing those two. I kept doing this until I wrote this talk, and I had to go back to the slide like 3 times. For some reason, it did not stick out, to the point that I think some of the collection instrumentation collection macro are called sample in my code because I could not remember which was which. Cool. I have a question. I can take it now before we go for the practice. I'm being asked what kind of impacts are to be expected from instrumentation profiling on the compilation time. Nothing that I could really observe. I mean, at least using Optick, the library seems pretty efficient to me. I always build, like locally when I build my game, unless it's an official Steam build or maybe like an overnight build. All the local builds I made, all made with instrumentation. I think it's akin to like compiling with or without asserts in terms of compile time, which is like some code will be or will not be if def in or out, and honestly, I can't really tell the difference. All right, let's talk about practice. So the first thing you need to do, going back to the question of happiness before, is to set up goals. you need to define goals. The first bit is set up a reproducible scenario. Profiling is just one thing you do during optimization, and optimization relies on reproducibility, because what are you going to do? You're going to tweak some code, you're going to run it, you're going to check if it's better, and you're going to try again. If you cannot get a stable metric in the first place, you do not actually have a way to figure out if a given change is better or worse. So that's basically goal number 0. Get a scenario that is reproducible enough. It is much easier in some cases than in others. For example, if you're having like a micro benchmark or a unit test or something like that, it is much easier to figure out, okay, am I doing better or not? If you have a whole application, you need to find a metric that works for you. And that is like, for example, in my game, the thing I usually look at is either the number of frames per second or the number of hours, in-game hours that I can take in maybe a minute, for example. That's kind of a metric I can use. And I usually try to stay within, I don't know, about 1 or 2%. I am not entirely, sometimes if it's only 1 or 2%, I'm not entirely sure that it's better or worse. It only depends. Like the better your, the stabler your scenario, the easier it is for you to figure out if you're actually making a change or not. So, right, you set up a reproducible scenario, you measure its performance, and you define an objective. We go back to the question of happiness. You need to have an objective, because if not, you're going to be there all night, and then the next month after that, like you need to figure out what is good enough, right? I mean, unless maybe your boss gives you like, maybe your goal is just optimize this application to death, and I'll just like, if the day you tell me it's done, I'm going to fire you. So then I guess maybe don't do that. But in most practical cases, you need to have an objective and say, once I've reached that, I'm good. I usually consider that the best is just to have a metric, like, hey, I want to do 60 FPS. I want to be able to serve like 100 requests in a minute, something like that. You need a target just to make sure that you do not fall into the rabbit hole and never emerge from it. And then you need to pick the right tool. My recommendation is instrumentation. I am really fond of instrumentation. Last year, my talk was all about using a sampler. I met somebody after this talk who told me like, hey, why are you not using Optick? And I don't want to go back. I mean, there is some very good things about sampling. We'll see that later. But I really love the added value of instrumentation, because once it is set up, it is really fast, and it allows me to eyeball very quickly if I can get an idea of a program. It has a cost, of course. Sampling alone is cheaper. If you have to provide something once and you're never going to go back to it, then sure, sampling is the way to go. You don't have to recompile anything. You just run it to get an ID. But I would ask you to consider that it's kind of an investment, right? Every time you add a bunch of consider it as an investment, because every time you have to go to your program and add a bunch of instrumentation callbacks, it's probably some time for the future. It's probably a bonus for the future, because future you, or another future you, a developer future you, maybe another developer, will probably need to debug this thing again in the future, profile it again in the future. And if it's already there, the only thing it has to do is just run the application. So there is a cost initially. You don't have to pay all of it. You can probably just make it for the very, very simple thing, like just the skeleton of what your application is roughly doing, the base update cycle. And then whatever you're trying to debug or profile or optimize. And then in the future, you revisit that and you just grow it. You know, like you just invest by adding more and more things. It's to the point that, you know, we had to pay the first cost at Paradox, for example, but the base engine is always have instrumentation now. And now every game, like I think I had to do it for a secret project. I can't talk about the details recently, just to have a rough outlook of how it's looking so far. And it took me maybe an hour to maybe less than 30 minutes. I don't know, but I knew the global model of the thing. And I just went there and said, okay, I'm just going to annotate the thing that I know probably there, and I'm just going to be able to have very quickly an eyeball of the results. But I think enough of all that technique, like vague talk. Maybe I should show you how it looks like. But let me check if you have questions first. Is Valgrind a profiler, and if yes, which type? I wouldn't say Valgrind is a profiler. Valgrind, I'm not sure how you pronounce it. I think it's Valgrind. I won't call it a profiler. I think it's more of a sanity. It's more like a sanity checker. To me, I use Valgrind to find memory leaks and buffer overflow, like basically unsound memory accesses and profile. There is a profiler called ColdGrind, I think, that is a subset of Valgrind or a companion library. I have not used it, but I think ColdGrind is a profiler. If you were unaware of Optick, how did you frame profile in vTune? With great difficulty. With great difficulty is my answer. There is an instrumentation support in ColdGrind. In vTune. I used it. It's supposed to be able to annotate frames the same way like instrumentation profilers are able to do. I think it's basically unlegible. It is vTune is slow. vTune is heavy. It is good, but it is very heavy. And I think that it is so heavy that I only want to use it when I want the actual very detailed information that it provides. But to eyeball, I didn't find it great. And also, yeah, the visualization is really bad. If you want to see like actual instrumentation, even with the instrumentation support that is in vTune. I have my library is able, like my macros in my game are able to switch between either vTune or another profiler. I started with vTune. I converted everything to Optick real quick because I didn't like the outputs. Next question. How is Perf a Perf a sampling profile tool? Yes, Perf is a sampling profile tool as far as I know. It does exactly what sampling does, as far as I know, but I'm not 100%. I have read people saying that it's something about an automated. It may have a mode that is like automatic sampling. Automatic instrumentation, where it basically inserts stuff at every at the start of every call stack. But I have not used it much, so I wouldn't be 100% certain. The best way is to discuss this after the talk, and I can double check for you. Do you know about Cause by Emery Berger and related? What do you think? I've seen his talk last year about the effects of how you can get very different performance result just depending on how your program is compiled and linked. I think I have checked one of these tools, but it was very Linux focused, and I am mainly shipping on Windows, so I did not go further than that. Sorry. Next question. Have you ever experienced instrumentation profiling itself causing bogus timing results? In your experience, have you found tool that may affect real world performance results? Yes, I have. For example, Optick has a small tendency to, I don't know if it's just resource leaks or if it's just the overhead of having of collecting the data. But I have seen cases where I should have theoretically a perfect 16 core occupation with 16 threads. And what I see that there is lock contention, and at some point one of the threads is doing nothing or is taking a long time to finish an operation, and there is no reason why it should. And when you look at the details, it tells you that basically, actually, out of the 16 score, you only got 15, and the last one was busy doing something else, which actually giving you the impression that one of the 16 tasks you ran was super slow for no good reason. So you can have some bias like that. I only saw it when I got to the limits, which is basically trying to perform something that was 100% core occupation. And yeah, you need a core somewhere to be able to record. And especially when I'm going to do this presentation, you need one core to be able to encode the video, play music, whatever else you're doing. You can limit that because there is a network option on Optick, which allows you to run basically it works with networks. It was with network, so there's a local daemon running on your program when you run it with Optick, and then you can connect to it with an external machine and collect. And I would suspect that this allows you to have a machine that has nothing else running and avoids that effect. But I haven't tried that personally. I brought up the cause profiler because it's a super nice piece of instrumentation. Okay, well, I'll have a check after this talk. Thank you. Any recommendation to profiling the compilation time? Yes, I would not recommend using a profiler. Most compilers nowadays have diagnostics that allow you to display the graph of what took time. For example, like which files or headers took too long to compile. This is outside of the scope of this talk, so I'm not gonna delve into it. Right, time for live demo. Finally, so. Here's my game. It's Hearts of Fire and 4. It's a strategy game about World War II. This is a very hot build that I made this morning from the unreleased version yet, so feel free to find leaks. I'm just going to start a game. If you want a more in-depth explanation of how the game plays and works, come to my talk tomorrow where I explain a bit more the base model of the game to show you basically how the performance works. What I'm going to do here is I'm going to disable some frame smoothing because it actually, sorry, thank you. And I'm just gonna run the game at maximum speed and I'm gonna connect to it with Optick. And I'm gonna look at what the results are. So here's Optick. It's just, it's very well titled, What the Hell is Going On? Because it's basically what it is, right? You have, okay, something is going on, what is it? So I'm going to unpause the game. You can see that the time is ticking. It's trying to simulate the world as fast as it can. And then I'm just going to record it. You can see that it's recording the frames. And I'm going to stop it here. We don't need more than that. And I can pause the game because we don't need it anymore. There we go. Sorry. It's as it is processing the results, it frees the window. And there we go. It's quite fast, as you may have seen. Did not take long. And I immediately got a profile out of it. And as you can see, I can just take a look, and you have basically the idea of what my program is doing. So you can see that every base frame is running here with the timing it is. It is actually quite slow compared to usual. I think it's a side effect of me trying to present the demo and everything. I'm expecting the frames to be a bit slower than this usually. Not by much, but a bit slower on the 16-core machines. But you get the rough idea. It tells you the time of every frame. And then you have a spike. As you can see, there's a spike every 24 frames. It is not completely by surprise. All games runs with a 24 like updates, simulates the world by the hour. And on the midnight tech, it actually does some extra computing, so you can see a spike every 24 hours. It is a known artifact of the way we design things. And if I decide to zoom on one given frame, I don't know, this one, for example, the game tells me exactly what's happening, right? So we are processing a CPU frame, we're executing the command, we are processing the early update, and this bit is taken by the supply system. This is the weather simulation, the air simulation, the country simulation, and then the AI. And then you see like the update of the graphics and the rendering. And if you go down, you can see that some of the threads are also being used. We have 15 worker thread in the main thread because it is a 16-core machine. And you can immediately see the results. And you can zoom in if you want to get more detail about what's happening. This is all stuff that we have added over the time because it helped us figure out what's wrong. And you have at the top, the very handy chart that gives you a hint of how many cores are being used at the time. I can see that not all the cores are being used, and I suspect that it is due to the fact that I'm also recording at the same time and a bunch of other artifacts. I have a few safe profiles after the thing to show you. But you can see like, yeah, when it's big, high bar, it means that we're burning through the threads. When there's lots of red, there's probably a bunch of contention, synchronization, or not much to do. And when there's only one, it's basically the code is single threaded at this point, and this is why it's taking so long, for example. Sadly, the units update in the game are not parallel, so you can see how it's taking 3 milliseconds while we can simulate stuff on many more cores at other places. So right there, you have a pretty good view of what the thing can do. And to show you that, for example, at some point you run out of detail, but you can still find more. If I find country serial update, for example, doesn't give me any details of what's happening. but I can click function flame graph here. And if I expand this a bit, it will actually show me stuff that it figured out by doing the, it can actually show me the frame graphs of the same code, of the same frame, but this time using instrument profile sampling. So even if I don't have, if I have not had it something, and it just, as you can see, it's basically inferred from the signatures, you can see what's happening. For example, we have, well, we're checking if we can produce some kind of equipment, which is done by doing some kind of script system, and you can see that it's trying to evaluate some triggers and entries. And you can even say at some point it's doing like it's doing free, it's doing malloc. You can see all that. So it gives you an idea, and you can delve kind of deep into what's happening there. And it has a few things that I really like. For example, one of the things I wanted to show, if I can find my thing here, yeah. If you click on a given frame, on a given function, for example, I don't like the air update, you get you see that each frame is there. You can get the average in the middle. You have the work time and you have the wait time, and you have the averages, which allows you to see, okay, am I stable or do I have outliers? And if you have an outlier, you can just click on it and see what's going on. For example, we can see that this one had, what was happening? Well, yeah, apparently just one of the thread got stalled, and I suspect it's just because some artifacts of for like a context permutation or something like that. I'm not 100% sure, but that's just my suspicion here. Right, so that should give you like a hint of how it looks like. I'm not gonna delve too much into this because I'm more here to explain to you the basic idea of what is profiling and what can you do with it. Did I have to instrument all these functions we see in the profiler? Asked the question. I had to do all the ones that are there, yes. And by that, it means I just added a code macro on those somewhere in the code. All the ones that you see in the flame graph are automatically generated by the call, by the sampler. So it's something that took me like, I don't know, there's like maybe 20, 50, 100 there. Took me some time. It was not all of them immediately. We added some on the go. Actually, I think we cheated. We had an in-game profiler. We replaced it with that. So we just found all the call sites when we had our in-game profiler, and we just replaced it by just register yourself to the instrumenter, and then we're done. All right. So it's all about finding the needle, right? Like looking at a profile the first time can be overwhelming. You have to look at what sticks out. And usually domain knowledge is key. You have to know your program. A profiler can tell you what takes the most time. It can explain why, but it can't tell you if it should take so much time, right? It's gonna say, hey, you have this function, it's taking most of your time, and maybe it's doing it because it's using a lot of CPU cycle. Maybe you have a lot of cache misses, whatever, you name it. It can't tell you if that's expected or not. Maybe you're actually doing some heavy computation and you don't have a very better way of doing it, but maybe you don't. And that comes to you, the programmer, being able to hunt the discrepancies and finding it out, right? And I think that's why I like those profile outlines, because once you know them, once you know what you have looked at the outline of your game or your program once or twice or 10 times, whatever, finding regressions is super easy, usually, or quite easy, because you know what it looks like normally. Someone reports that the program is looking slower. You just open it and say, hey, I'm not used to see that thing being so big. What's happening there? And basically, it's all about figuring out what takes time versus what should take time. I have a quick example. I see a lot of questions. I'm going to have to take them after this because I see that we only have 20 more minutes to run, and that is a bit, that may not be enough. So for example, we introduced a bug 2 or 3 weeks ago. The game was having, as you can see, a very long frame time compared to usual. You know, the average is expected to be, as we said before, I don't know, 30 milliseconds maybe, and more like 50, 60 on every 24 hours. You can see that everything spikes. So I opened this with the thing, and I immediately saw something. You see this yellow bar that comes every 2 ticks. if I unzoom, you'll see it's probably a bit better. You can actually see it from here. The game rendering. You can see that one frame is fine. The next frame you have rendering that takes 30 milliseconds. One frame is fine. The next one rendering takes 30 milliseconds, etc., etc. Every 2 frames, suddenly the rendering takes 30 milliseconds, and if you zoom in, it's the manager that is supposed to handle the map texture, because we have, like, if you look at the game, we have a map with a lot of colors, and it's basically one big texture that we project with a 3D effect on the map. There's some clever shaders behind that. The way we figured out, it was super easy for me. I didn't have to hunt it for a lot of time. I just open this and say, hey, why are we re-rendering the map every 2 frames? There's something wrong with this. I just had to do a git blame or a git log on the file that is supposed to handle this and say, hey, we changed it 2 days ago, and someone tweaked the code that is supposed to determine if we should if the cache is dirty or not. There's probably a bug there. And then it was all about finding the bug in the code. But the profiler had told me where to look. The profiler's job was mostly done. I just had to figure out which condition was making the cache breaking. So the best work is no work. And so the most efficient code does nothing. And profiler can highlight user's computation. And that's basically what it did there. It just told me, hey, you're redoing this thing all the time. And since I had enough domain knowledge of the app, I knew that it was not something that was expected. We have a cache. It's supposed to be there for that reason. It should not be dirty every 2 frames. And so I didn't have to dive any complex metrics that would have sent me on a tangent. There was no point analyzing why it was slow. Like technically speaking, it was slow because it should not be cool. And that was the end of it. And that's where I think having this 2D visualization saves you a lot of time. So when you're profiling for the first time, I'm going to try hopefully to answer some of those questions as the talk goes. You assess the big picture. And again, if you understand the domain, this is key. It will help you figuring out where you should start digging. And again, get the quick wins out of the way before you delve deeper, right? If you immediately see something that you do not expect to be so this slow, and you can figure out that it's just something that should not be there because you have a cache that is broken or whatever else, just get that out of the way. And then once the noise is eliminated, you can start looking at, okay, what is standing out now? And that's where we go to profiling analysis, which is the third part of my talk. So you have a lot of metrics that are available to you in a profiler, especially something like vTune, which I will show in an instant. The basic thing would be, okay, for every function, like what's the CPU time, what's the wait time, and potentially what's the system time. System time, usually it's more visible as basically one of those 2 metrics, but taken by the system and not by you because you're in a system call of some kind. So I would probably put it that way. It is something you can see if you do like very basic time measurement applications, but mostly it's one of those 2. And if it's the system variant is just the one that happens in the operating system, not in your code, basically. So if you have high CPU time, what's happening? You may have some inefficient algorithms or some inefficient data structures. You may have spinlocks. You may have single-threaded code. You may have microarchitecture issues such as branch misprediction and cache misses. We'll delve through those in a minute. If you have a lot of wait time, you probably have disk I/O or network calls that are basically on the critical path. You may have locks. Mutex, basically synchronization primitives. That is usually the classic. Allocations is potentially another one, but most of the time it's CPU time and not wait time. It is only wait time if you're running low on memory and the operating system has to free something and give it back to you, blah, blah, blah. If it's just done inside the system library, it's going to be CPU time. I'm not going to delve into it too much right now. So to show you more of all those metrics, I'm going to open a capture of a profile I made earlier today that is done with vTune. It's the same kind of thing. I run House of Iron for about 10 seconds, as you can see here. And I just look at this. So you have a bunch of data. It tells you like how much CPU time was taken, how much effective time, spin time, and overhead time. Why is the CPU time longer than the elapsed time? Easy. I have 16 cores. So it's the total amount used by all the cores, which might actually be misleading, and we're gonna talk about it later. And if you look at what it looks like, you have the bottom up, which is whatever took the most time at the top. You have the kind of graph of CPU of occupation of your threads at the bottom, with green being nothing to do, brown being like CPU time, like you're chugging through something, and red being synchronization primitive or spinlocks. I think mostly spinlocks actually. And then you can sort by CPU time. And then there are other views that you can open that will sort by other metrics like sleep time, wait time, clock per instruction ratio, number of instruction versus the number of instruction used, that kind of things. This one is not the one. And you have the top-down tree, which is maybe the classic profiler view of a sampler, which is you start by the total, basically the entry point of your program. 100% of your program time is spent in the top. Now we say, okay, let's start from main and let's go under main, and then you get there and say, okay, under main we have 20% of the CPU is spent under main because it's the main thread. And then most of that time is spent into the idle thing, which is the main loop of the game. And you can see that we have about 2% of those 21% that are in rendering and 16% in updating the actual game simulation. Most of that being the simulation of an error. And then if we go down, you see, okay, simulating country is the top one, and then it's the supply system, and then it's the hourly error updates. That's the rough idea of what a profiler will show you. I'm not going to delve into it too much. Again, this is not a vTune intro. Just to give you an idea of what's there, I'm going to explain a bit more in here, a few things to note. So the first thing is that there's lots of metrics. Actually, I think maybe I should show it there. There's lots of metrics, but it's total CPU time, right? And total CPU time is extremely misleading on modern computers because you have 16 cores and you're trying to multi-thread stuff if you can. So you can have a high CPU time, but that's actually done like, for example, if you have a high CPU time, but you have like 16 cores, 100% used, there's probably not much to be doing there because that's not as big as a bottleneck of like the most of the cores doing nothing and one of them just trying to chug through data. You could transform that already. So one of the things I usually do is I immediately filter on the main thread here, which takes a minute or two to reload in vTune. There I can get something that is more like what you would expect as a programmer trying to follow the control flow, which is, okay, now I have 100% mainly in my update loop. And of that, 75% are spent in the simulation, and 64 of the total is basically in simulation of an error. And then you have like 30% in the countries, 18% in supply. You get the rough idea. If you want real time, there is another. When you configure what you want to do as an analysis, you can select various things, and you have one that is called threading that will give you the real time instead. I will go back to my slides. All right. So sampling aggregates call stacks across threads. Consider filtering on the main main bottleneck thread. Again, it is better to first analyze where your bottleneck is by looking at the 2D visualization, like this one. Figuring out, okay, this is this bit that is executed on this thread that is basically everything else is waiting on that to finish. That's my bottleneck. Then you start profiling that, and you can filter your sampler based on that analysis. And that's, again, 2D control flow is very good to figure out where you should actually focus your attention. We can now look at a few reports that I've taken either as a screenshot or just as an explanation, and give you a hint of what does that mean, what is the first thing you should consider, and what's going wrong. For example, here we have an inefficient algorithm. This is actually taken from one of our candidates. One of the tests assignment we give them is to write a pathfinder, and this pathfinder is the main loop of a very classic ACE pathfinder, in which you find you explore the nodes around you, you find the one that is the most promising. And then you recurse. Basically, that's the whole thing. So the loop, what does the loop does? If it has not found the end, you look at all the nodes you have found so far but not explored, and you say, okay, which one is the most promising, and let's go with that. And as you can see, 9 plus 33 plus 47. Most of that loop is spent trying to figure out what's the next best thing. And you can see it there. And what's the problem with that? Well, obviously, every iteration of the loop, you are trying to do a linear search through all the possible matches to find the best one. Your algorithm is not the best. You should try to find something that is better than a linear search. It is usually tied to the next thing, which is data structures. It's like, okay, can you find something that makes it at least n log n to find? Can you just have a sorted array, a heap? There's lots of data structures that can help you, but basically this is not efficient because you're doing a linear search every loop, and the profiler is telling you, hey, you're spending all of your time in those 3 lines. So basically, an inefficient algorithm is usually, the symptoms is that you have a lot of time spent in loop, like execution of a loop or a recursive call. Check the big O. That's the first thing. Like how is the big O? Especially if it starts going like square, cube, or even worse. That's probably where you have an issue because it's just not scaling well. And then figure out, okay, can I cache this computation maybe, or can I reuse it, or is there a better data structure that will not force me to use that thing? Is there a better algorithm to do this? Basically, data structures, inefficient data structure manifest to a similar way. I put them in 2 different categories, but it's kind of the same idea here. It's another pathfinder, and this one is trying to find the neighbors of a given cell to explore. And as you can see, a lot of the time, about maybe 45% of the iteration is spent on 3 lines, and those 3 lines have something in common. We're accessing the same data structure. We're doing a find here, we're doing a find here, and we're doing a square bracket operator here. If you look at this code more in detail, you'll figure out that this is a standard map, and standard map is a binary search tree, which doesn't scale as much as more efficient data structures, such, for example, as a hash table. So the symptom here is you have a lot of time spent on find, insert, or operator square brackets, which probably means your data structure is not optimized for the access pattern you're using. So it is easier to spot without inlining, although if you can see the lines by themselves, it's good. Sometimes you're lucky, it is not in line, and the profiler will just say, hey, the biggest function, the biggest single function that you keep calling all the time and it's slow is fine, and or insert or operator square bracket on map. That gives you a hint, but often it's in line. So you have to look at the actual code and say, hey, those 3 lines that are like the most heavy in the profiler, they're basically always doing, they're always using that data structure. So again, solution is know your data structure, your strength, and their weaknesses. Spinlocks will show also as a lot of CPU time. Modern profilers like vTune are able to identify it as spin time. If your profiler does not support that, you can usually guess that it's a spinlock by the name of the function. It's called like spin or like try lock or whatever. And it's like, okay, look at the bigger picture, look at the threading model. Basically, I am not here to give you a talk about concurrency. Locks are bad and try to avoid them if you can. That's the short answer. Single threaded code, you can see that because you have a function that basically is the bottleneck of your execution flow in the 2D variant. And while this is executing, nothing else is running. You have 16 threads on modern machines. You could probably do better if you consider the parallel algorithm or task scheduler or any other way of reordering the work to do the same amount but end up earlier. Microarchitecture usage, I am not going to talk about it much. This is basically when you have a high clock per instruction rate. This is delving into micro optimization. This is a fascinating topic. This is not a beginner topic, and this is not something you should start by looking at. It is important, but it is tricky to do on large applications. Keep it for last. If you have like functions that are highlighted by this, it is useful to know, but don't start there. Hopefully, there is another way of approaching the problem that will either make it go away. Because, for example, a bad data structure will also have a high CPI rate, but there is an easier abstraction to reason about that. there is good talks about micro optimization. I will not talk about it more here. Blocking IO, you basically have a lot of wait time on file system or network APIs, read, write, open, that kind of thing. First question you should ask yourself is, can I put this in an async task instead? You can see my talk last year. I'm going to put a shameless self-promotion there. I made a thing about making the game start fast, and it's a lot about doing the work in a different fashion. And there is one bit about that. This is a slide from my talk last year, and you can see, for example, here, another thing we have is platform grab mutex, 58 seconds spent waiting on the mutex. That's basically, you have a huge wait time on the synchronization function. When your profiler tells you that, you have a lock, and it should not be called a mutex, it should be called a bottleneck, because that's what functionally it is. Again, I am not here to tell you about how to solve all those problems. I'm mostly telling you this is how you identify them or get a hunch that it is the problem. And then there is much better sources online and offline to explain you how to fix it. Again, consider another concurrency model. Take a look at my talk last year. There's also lots of great talk at CppCon that can help you figuring out how to solve this. So in general, the profiler will show you what sticks out. You will need some filtering to be able to focus on what is right. And it's up to you then to figure out, okay, I've shown some stuff. I have an idea of why this is the case, and then you can try to work your way, how can I solve it? I would suggest you, just as a very simple optimization principle, start with inefficient algorithm, inefficient data structures, and locks. This is probably the first two are the easiest. Locks might be a bit trickier depending on how well you're allowed to change the execution flow of different threads and stuff like that. But that's the three things you need to change. That's probably the easiest bits. If you start going into micro optimization territory, things are going to get harder, and especially with a bigger application, it's much harder to visualize. Right, so I'm going to have to conclude there, and then I will see if I have some time for question. If not, don't worry, we can continue talking in Gathertown as with the other talk. But if I have to do a conclusion, profilers are here to help you pinpoint performance bottleneck. That is what they do. They don't solve them for you. They are just a tool that helps you saying, hey, you probably should be looking there. Domain knowledge will help you. The more you know about how the application behaves, what does it mean? If you have an intuition, what does it mean to simulate the weather or the supply system or process a client request? What's the kind of work that this thing should be doing? Then you can say, okay, that sounds about right, the fact that it's using that much time. Or, oh, wait a minute, why is it taking that much? It shouldn't be. So that's the thing. And finally, I would really recommend you to add instrumentation support to your program. It is a cost at first, but I think in the long run, it really helps visualizing what your application does in a much better way than a sampler. Sampler are great to analyze stuff in a very, very, very focused way with a lot of metric, especially vTune. I just don't find them super great at showing you the big picture with a nice visualization. Optick and a lot of profiler made for games have a very neat visualizers that I really, really like. And furthermore, I think your build should be destroyed. Thank you.